So we were doing the following problem. Our purpose was to find what is the rate of change of the water elevation with time. So what we did is that we applied first the continuity equation, and this is what we obtained. By applying the Reynolds transport theorem, where beta is equal to 1, we obtain the continuity equation. Then if we do the analysis of terms, first we did the derivative with respect to time of integral control volume rho dv, which represents the change of mass in our control volume. And we divided into two parts, volume 1 and volume 2. Okay? Now, we were talking about when we can neglect this term compared to this one if we have a very large variation in densities, because the density of air is much smaller than density of water. But here in this case, even if you don't have density of air negligible with respect to density of water, this term is 0. Why? Because let us do the analysis of each term. When we did rho w times area of the tank times h, this represents the volume of water times h, which represents, when we multiply the volume by rho, this is mass of water in our tank. And the second term is rho of air times volume of air. So when we do rho of air times volume of air, we find the mass of air in the tank. But as you can see here, your tank is closed. So if you go back to your figure, what do we have? We have a closed tank that contains initially air and water. So as water will enter the system, what will happen is that the mass of water is increasing. But what about the mass of air? The mass of air will remain the same. So what will happen is that the volume of air will decrease, but due to compressibility effect, the density of air will increase in a way that the product rho of air times volume of air will remain the same. And therefore, here, even if I have another fluid for which the density is not negligible compared to water, I will still have that this term is constant. So when you derive a constant, you will get 0. So this term will cancel out, and I will only obtain that the change in mass of water, okay, is equal to sum of m dot n. Because if I take this term to the other side, I will obtain the following. I will obtain that rho water times the cross-sectional area of the tank times dH by dt is rho 1 A1 V1, which is the mass flow rate coming in from section 1, plus rho 2 A2 V2, which is the mass flow rate coming from section 2. And here, since I don't have any outlet for water, so of course water will accumulate in my tank, and I don't have any m dot out, so I just have 2 inlets here. Now I have everything, all the information needed are given. I have the velocities, I have the cross-sectional area of the tank, and concerning A1 and V1, I know that the inlets are of circular shape, so their cross-sectional area will be the area of a circle. So to find A1, it's pi times d1 squared over 4. And similarly here, the value of A2 is pi d2 squared over 4. So now I'm ready to find how the height of water is changing with time. Okay. So as you can see here, by simple replacement, dH by dt, if you replace your parameters here and you look at your expression, rho 1, rho 2, and rho water, it's the same value because I just have water here. So rho 1, rho 2, rho water, it's the same variable, which is rho of water, and it's constant. We are dealing with an incompressible fluid, so we can simplify it. And then what do we obtain? We will obtain that the change in h with respect to time is A1V1 plus A2V2 over the cross-sectional area of the tank. And A1V1 represents a volumetric flow rate. The volumetric flow rate, which is in meter cube per second, represents the change of the rate of volume entering and exiting my system. Here I don't have exiting rates, I just have entering rates. So the volumetric flow rate, Q, you know it in general we represent it as Q, is just A times V. And you can verify units. So the cross-sectional area is in meters squared. The velocity is in meter per second. So the volumetric flow rate will be in meter cube per second. And now I can find what is the resulting change in h with respect to time. And the unit will be, since I'm dealing with English units here, dh by dt is like a velocity. So it's feet per second. So when you work with English units, it's feet per second. If you are working in SI units, it's meter per second. Now, in particular, okay, in majority of cases, we will deal with 1D inlets and outlets. So when they say this, what do we mean by this convention? So when I talk about 1D inlet and outlet, then I consider that the velocity is uniform over the area of my control surface. Okay, so it's true that it's not always the case, and we will see what to do if it's not the case. But in case we have an application where this assumption is valid, so let's say you have uniform velocity profile. And in general, this assumption becomes valid, you know, in which case when I have the inertia forces dominant over the viscous forces. So when we talk about change in profile with respect to the cross-section, this is due to viscous effect. So when the inertia forces are dominant over viscous forces, then your profile will nearly be uniform. Okay, and then you can consider that I have one velocity over the cross-sectional area. However, for laminar flows, where Reynolds number is not very high, as we will see in next example. So if you have a tube, you have a flow in a tube, then if it's a laminar flow, we'll have a development of a parabolic profile for the velocity due to viscous effects. So due to viscous effects, you will have gradual change in velocity within your fluid. This is the effect of viscosity. However, in case the inertial forces, so if the velocity is very high, Reynolds number is very high, then the inertia forces will be dominant over the viscous forces. And in this case, you will just observe a small transition at the wall level. So, but it will directly go from 0 to V. This is why we can consider it's nearly uniform. So this will depend on the type of flow, if it's laminar or turbulent. Okay, and this will be clear in the given. So in case they told you in the given you have a highly turbulent flow, or you can consider that the velocity is uniform over the area, then this will simplify things, because you don't need to integrate anymore, because you know that these terms m dot in, m dot out are due to the integration over the control surface. So if we go back to our theorem, so we are applying the following theorem here. We are applying the Reynolds transport theorem for continuity equation. Okay. So if you look at the following formula, this term represents the integration over the control surface of the velocity profile. So in case I have the velocity changing over the control surface, I need to do an integration. But if it's constant, this will simplify a lot my analysis, because if it's constant, I can take it outside of the integral. Okay. So now, for the next step, what we will do is we will consider what will happen if the velocity is constant and what will happen if it's not. So if it's constant, as we said, we can take it outside of the integral. And if you are dealing with an incompressible fluid, also rho can be taken outside of the integral. So what will happen is that when I go to the following term, okay, I will get rho times V times A. For an inlet, it will be positive. For an outlet, it will be negative. Why? Because you know that when the term was on this side, okay, I have plus integral over the control surface of rho V dot N dA. We said that when we have an inlet, we have that V dot N is negative, while when we have an outlet, V dot N is positive, because if you go back to your tube, for the inlet, you have, this is your normal vector. Your normal vector is opposite to the velocity vector, while for an outlet, the normal and velocity are collinear, okay, and same sense. So when you do V dot N for an inlet, you will get a negative result. When you do V dot N for an outlet, you will get a positive result. But when you take the terms to the other side, then you will get plus the inlet flux and minus the outlet flux. So what will happen then is that this is M dot N, this is sum of M dot N, and this is sum of M dot out. And since we are considering constant density because it's incompressible fluid, we were able also to take rho outside of the integral. So then by taking rho outside and taking V dot N outside, we'll get just integral dA. And integral dA is the area. This is why we say that when I have a uniform velocity profile, I can just say that the transient term, which is the accumulation of mass or loss of mass within my control volume, is just equal to sum of M dot N minus sum of M dot out. And now, in case it's a steady flow, so if it's steady flow, then the transient term will cancel out, and then I will just obtain that summation of M dot N is equal to summation of M dot out. And this is the case in general for, so if you have a piping network and you want to do analysis of it, in general you deal with steady applications. So you have several inlets, several outlets, and you will use the following concepts to find how the mass will be distributed. So you have conditions that summation of M dot inlet should be equal to summation of M dot outlet. Now, what if the velocity profile is not uniform? So if the velocity profile is not uniform, you should then consider to do integration over your area, okay? As we said, this is typical case for a laminar flow. So you have, if you have a laminar flow in a piping system, then what you should do to be able to apply continuity equation, you should integrate over your inlets and outlets. So for example here, let us say this is an outlet, and we want to determine what is the total mass flow rate over this outlet. So we'll apply the following equation, that M dot is equal to the integral over the control surface of rho times VR dot N dA. Okay, so if you remember, we said that we should use V relative because we consider the velocity of the flow relative to the control surface. But in general, if we deal with a fixed surface, so if the surface is not moving, then VR is equivalent to V, to the absolute velocity of the flow. While if the surface is moving, we should not forget to subtract from the absolute velocity of the flow the velocity of the control surface. Okay. So now, in order to compute in this application for a fixed pipe, what is m dot outlet, V control surface is 0, and since it's an outlet, V dot n is equal to V, okay, because you don't have you have an outlet, so both V and n have the same sense. When you do V dot n, you will get V. So this is V, and you have now to integrate over the area VdA, because rho is constant since it's an incompressible fluid. I can take it outside of my integral, so I just have now to integrate the following term, the integral of VdA. Now, what I should do to be able to get this integral, I should know how my velocity is varying within my cross section. What is nice here is that I have a symmetrical profile. Okay, due to symmetry, if I look from the side view here, I have the following. I have a circular cross section, and velocity is only varying in one direction, which is the radius. So velocity is only varying along the radius, but it's not varying along theta, the angle. This means that if I consider any thin element, okay, at a fixed distance from the center, the velocity is the same across this element. Okay, so any point I consider on this element will be characterized by the same velocity, because the velocity due to symmetry is independent. This is we call it an axis symmetric flow. The velocity is not depending on the direction. So whatever is theta for the same r, the velocity is not changing. Okay. Then I can consider that the velocity is function of r only, and it will be a constant over this area. So the elementary area dA that I will consider is this one. And what is dA here? dA here is equal to the perimeter of the following circle times the thickness. The thickness is dr. So dA will be 2 pi r times dr. Okay. And now, if I just replace here, all I need to know is how U is varying with R. So as we said, for example, for a viscous laminar flow, you have a second degree variation. It's a parabolic profile. So I will give you then the profile of velocity along R, and all you have to do is to replace V function of R or U function of R and integrate over R. And this will allow you to calculate your mass flow. So until here, we have considered applications for the continuity equation. So this is the first conservation law, which is the continuity equation. Now we will move to another very important conservation law, which is conservation of linear momentum. And conservation of linear momentum will be used a lot in fluids. So whenever I am interested into what are the forces acting on my system, I will need to deal with the conservation of linear momentum. And this is equivalent in dynamics to the second law of Newton. Okay, so if I want to apply for a fluid what is called the second law of Newton, or the conservation here of linear momentum, I will have to go back to the Reynolds transport theorem. So going back to our initial slide here, and this time I will replace the variable beta by the velocity v of the fluid. So what do I obtain then? I will obtain del by del T of mv. mv, if you remember, is called, this is the linear momentum of a particle. This is called the linear momentum. Okay, so I should determine then how the linear momentum of my system is varying with respect to time. This is the purpose of my equation. So now if I replace beta everywhere by v vector, let us do an analysis of the terms that we will obtain. Okay, so here beta also is v. So let us see each term will represent what. Okay, so first, this is del by del T of mv of the fixed system. This is variation of linear momentum. And this is defined as summation of external forces. Because if you go back to the initial definition of the second law of Newton, you are familiar with sum of forces equals to ma. Okay, but sum of forces equals to ma, which is the case for rigid bodies, is derived from this relation. Because for a rigid body, okay, what is A? A, you know that A is dv by dt. Okay, when I deal with a rigid body, the mass is not changing. So when we deal with solids and we want to apply the second law of Newton, the initial expression for the second law of Newton is that sum of forces is equal to the derivative of mv, which is the linear momentum, with respect to time. But when I deal with a solid, when you derive u times v, you know that the derivative is equivalent to m dv by dt plus uv prime, so now plus dm by dt times v. Okay, but for solids, the mass is not changing. This is why this term cancel out. And for solids, you only have that sum of forces is equal to m dv by dt, which is equals to m times acceleration. However, for fluids, it's not the case, because here, when you consider a control volume, we said that the mass can be varied. Okay, so now when you apply it for the system, okay, when you apply it for the system, the mass of the system is fixed. It's right. This is why for the system, okay, this term will cancel out the m by dt, and I will just have m times dv by dt, which is equal to summation of external forces. But now if you want to do the interpretation with respect to the control volume, for the control volume, the mass is changing. So when I deal with the control volume, I will have to consider the transient term, which is related to del by del T of integral of the over the control volume of rho v dv. And also I have the term of integral over the control surface. And how we can physically do the interpretation of these terms. So the first term represents the momentum accumulation or loss in the control volume. So it's similar to the continuity application. This term, when we did the continuity equation, this term represented the variation of mass within the control volume. So if mass is accumulating or if mass is lost. Okay. Whenever you have accumulation, this result will be positive. Whenever you have loss, this result will be negative. So here, since we are now applying for the variable of v, our variable of interest, when we multiply m times v, we get the momentum. So now this will represent the momentum accumulation or loss in the control volume. While here, you will have momentum fluxes that are coming in and getting out of your control volume through your control surface. So like it's similar to m dot in, m dot out. You have also now here, you have fluxes of momentum. So you have m dot v in and m dot v out. Okay, and then this term here will be the total summation of all external forces. So we can say that for a control volume, when we do the analysis on a control volume, the sum of external forces acting on our system will be equal to momentum accumulation or loss in the control volume plus the fluxes that are entering and exiting the system. Okay, so now let us do interpretation of what are the possible forces that can act on our system. You have variety of forces. You have all forces that can be applied on your control volume include the pressure forces, the viscous and the shear forces, which are equivalent to friction. You have also the gravitational forces, which are body forces in general, and they could be magnetic, that could be electric. You have the surface tension forces, and you have solid forces. So when you have a control surface cutting through a solid object. So we have a variety of forces that can be applied on our control volume. So to know what to do, we should look at our problem, draw the free body diagram of our system to determine what are the dominant forces acting on it and which should be considered. Now, let us do a small example on this. So before going to the example, remember always this relation can be simplified in case of simple examples. So in case you have a system where you have 1D inlets and outlets, and you have a non-steady control volume, your equation will be written as follows. So you have summation of external forces equals to, so the accumulation term will remain here, and we should see how to deal with it. So del by del T, this term is present whenever you have a transient application. So when you have transient application, and when you have, therefore, variation within your control volume of the momentum. So when you have change of velocity with time or change of rho with time, this can lead to this transient term. And now concerning the fluxes of momentum in and out, so we said if we have 1D inlets and outlets, and we consider, when we say 1D, if you remember, we are talking about uniform velocities. So when I have a uniform velocity over my cross section, what will happen? Again, I go back to the formula. The formula is here. You have integral over the control surface of rho times v dot n dA. Okay, and here in addition you have times v vector, because now we are dealing with beta equal to v. So when you apply the conservation of linear momentum, your flux terms will be as follows. It will be integral v times rho v dot n dA. What will happen if my velocity is constant? If I have a uniform case, okay, I have a uniform velocity over the cross section. First, v dot n, okay, since v is constant, v dot n for an inlet will be minus v, and for an outlet, so it will be minus vn for an inlet and plus v out for an outlet. Okay, and since I'm dealing with incompressible flows, rho is a constant, so I can take it outside of the integration. Now v vector, okay, for v vector also it's a constant since I am considering a 1D flow, so uniform velocity profile, so constant velocity vector. So everything can be taken outside of the integration. So if I have an inlet, this term will lead to minus v inlet times rho, okay, times the inlet velocity vector times integral of dA. And integral of the A, since I am integrating over the control surface, integral of the A will give me the area, will give me the total area of my cross section. So now, let us look what do we obtain. If I take A with rho times V inlet, I will get M dot inlet. So this term will end up with minus M dot inlet times the velocity vector at inlet. And similarly, if you do the same analysis for an outlet, you will obtain plus M dot outlet times vector velocity at the outlet. Okay. So now, if you have several inlets and outlets, you will just have summation. So minus summation M dot in Vn vector plus summation M dot out V out vector. And then if I replace them in my formula, I will get the following. I will get that this term can be represented by summation of at outlets of M dot times V minus summation at inlets of M dot times V. And in the particular case of steady control volume, okay, so if I don't have motion of my control volume, okay, so then I don't have, if you want motion, and I don't have change in density within my control volume. So this term is steady, del by del T is 0. Then I can say that sum of forces on my system is equal to summation of at outlets of M dot V outlet minus summation at inlet of M dot V inlet. So please keep in mind, whenever we say steady in dynamics, for you steady is 0 acceleration. So sum of forces equals to 0. It's true for solids. For fluids, when you have a control volume, even if your control volume is fixed or it's moving with constant velocity, okay, this does not mean that sum of forces on it is 0. You will see that change of momentum of the fluid, okay, within the control volume will lead to certain forces acting on it. And now when we go to some of applications, you will understand better this. Okay. So let us start by a simple example. I have a fixed control volume. So maybe when I tell you it's fixed, you can consider, so it's not moving, no acceleration, sum of forces equals 0. It's wrong. Why? Because this is valid if you don't have flow coming through it. But when you have flow that is trying to move through it, if your system will remain fixed, you should have forces developed on it to balance the change in momentum through the control volume. Okay, so a fixed control volume of stream tube in steady flow. So here also the flow is steady, V is constant. So also maybe you will think V constant and in magnitude, and the control volume is fixed. So of course it's the sum of forces 0. Also no. Okay, we'll see why. So we have a steady flow that has a uniform inlet velocity ρ1 a1 v1 and a uniform exit flow ρ2 a2 v2. Find an expression for the net force acting on the control volume. So what will happen here, we are in a steady application. Because everything is steady, the conditions at the inlets are steady, the conditions at the outlets are steady, our control volume is fixed, okay? Then the transient term of sum of forces is equal to 0. But we should pay attention at the other term, which is the change in momentum, because we have fluid momentum fluxes that are coming in and momentum fluxes that are going out. So let us look at our control volume of interest. Okay, this is our control volume, and as you can see, we have first an inlet here, and we have an outlet. Okay. Now, since it's a steady flow, what I am sure about is that M dot in, so what is coming, you know that whenever I have a steady application, as we have seen in the continuity equation, when the transient term cancel out, this means that summation of m dot in is equal to summation of m dot out. And in this problem, we just have one inlet and one outlet. Okay, so just we can write here that m dot in is equal to m dot out. So we can find a relation between V1 and V2 using the continuity equation. The relation will be, if I replace m dot n by rho times V1 times A1, this is m dot n. Okay, to remember, V1 A1 represents the volumetric flow rate Q, so Q1, and rho is the density of my fluid. And since here I'm dealing with incompressible fluids, so you can say also or m dot is conserved, or you can say that the volumetric flow rate Q dot is conserved also. Okay, so I have rho V1 A1 equals to rho V2 A2. So now I can simplify the velocity, the density term. So I get the relation between velocities V1A1 equals to V2A. So if I have constant same cross section A1 equal to A2, then V1 will be equal to V2. If not, I should calculate then a relation between V1 and V2. So I can say that V1 is equal to V2A2 over A1 over A. Okay, now let us do some analysis. In which cases sum of forces will be zero on my control volume? If I have change in direction of the velocity vector, so of course I will have a net force that is not zero. Because you know why? What you will do here, you will do sum of forces equal to the outlet momentum flux, which is m dot 2 times v2 vector. Here I can use this expression without integration. Why? Because they said that the velocity is uniform over the cross section. So since the velocity is uniform over the cross section, no need to perform any integration. The outlet flux, the outlet momentum flux is m dot 2 times velocity vector at cross section 2. So here, if you want, how you know that these are vectors? They are using bold letters. So you have several notation for vectors. Vectors can be represented with an arrow above the letter, or also you can put it as a bold letter. Whenever you see a bold letter, so this is a vector. Okay, so now the expression of sum of forces is equal to m dot v2 vector, which is the outlet flux of linear momentum, minus m dot 1 v1 vector. So since m dot is constant, we said that m dot 2 is equal to m dot 1. So I can take it into factor. So m dot, so sum of forces is simply here m dot times v2 minus v1. So the only case for which sum of forces will be zero is when the velocity vector 2 is equal to the velocity vector 1. So this is only applicable if you have a tube that is rectilinear. So if I have a rectilinear tube, okay, or I can have it curved if you want, but it should be curved in a way that, so for example, like this. This is a curved tube, but at the inlet and at the outlet, the velocity vector is the same. Because what is the condition to have same velocity vector? First, same cross-sectional area. So here A1 should be equal to A2. So if you have, if you want same sense but different magnitudes, because if I, let's say, if I do this, I can put a larger area here. If I put a larger area here, then V1 vector is different than V2 vector. So the only case where sum of forces equal to 0 will be when I have V1 vector equal to V2 vector, okay? Which means that I should have the same cross-sectional area at the inlet and at the outlet. If I'm just having one inlet, one outlet, of course, okay? If I have several inlets and outlets, it should be in a way that the summation of m dot inlet v1 inlet equals to a summation of m dot outlet v out. So if the condition is satisfied, then I have sum of forces equals 0. If not, I will have a net force acting on my control volume. So here, for example, of course, it's not possible to have sum of forces equal 0, because even if A1 equal A2, which will lead to the magnitude of V1 equals to the magnitude of V2, the direction is not the same. So as you can see here, V1 direction is different than V2 direction. So here I can be sure that sum of forces will not be 0. And how I can physically do the interpretation of this? You need, whenever you have a change in linear momentum, you need forces to do this, okay? So whenever, if you want, summation of forces is due to two things. If I am accelerating with time, okay, if I have a transient term with time, or even if I have a steady application, if I have a change in linear momentum within my control volume between inlets and outlets. I will give you an example to understand it in a better way. So let's say you have, imagine that you have a certain pipe that is fixed. When you are putting a flow that is coming in over it, okay, it will tend to move the surface with the flow. So if I don't have a support that can react, my surface will move. Okay, this is why we say that this surface to be fixed, and this is the case here. We are dealing with a fixed surface. If I want to keep it fixed, I should develop a force on it that will oppose the coming flow. So it will oppose the entering momentum. This is why here you have minus m dot inlet times v1, because if you have a support here, this support should try to oppose the action of your inlet fluid. However, imagine that you have a flow that is going outward of a system. This the outward flow will tend to push the system backward. It's like if you want the rocket. If you remember for the rocket, what will happen for the rocket? As gases will go out of the rocket, you will have a force that will push it upward. Okay, so here, if you want to maintain your control volume fixed, you should develop a force in the positive direction. This is why here you will have, which is equal to which is the same direction of the exiting flux. This is why if you interpretate this relation, you will have plus m dot v outlet minus m dot v inlet. Okay, so you need forces to balance. These forces applied on the control volume should balance the change in linear momentum crossing the control surface of our control volume. Okay. So as we said, the resultant forces that should be applied on the control volume to keep it fixed is m dot times v2 minus v1. And we can do the interpretation that this term will represent the net force acting on the control volume that is needed to balance the change in momentum of the fluid as it's turning and decelerating while passing through this control volume. So whenever I have change in direction, or whenever I have change in magnitude of the velocity through my control volume, I need to have a net force acting on my control volume. Now, another important application for momentum is the equation of motion for flow in a duct. Okay, so if I have a pipe and I am interested into the variation of pressure within this pipe, because you know, whenever you design a piping network, okay, you should, let's say, know if I need a pump to be used, what should be the power of this pump, etc. I should understand what is the factors affecting pressure loss through my system. So you know that as a flow will go over a certain pipe, we'll have a pressure drop, we'll have pressure loss, okay? And we need to quantify this pressure loss to be able to design our piping system. So for example, here, we will develop an expression for pressure loss for steady, fully developed flow in a circular duct due to frictional effects. And they told us to neglect gravity forces. So what is happening here? First, when they say it's a steady flow, okay, steady means that del by del t, any term that is transient with respect to time will cancel out. So whenever you see the term steady, then you will cancel out del by del t in your continuity equation and in your momentum equation. Then it's fully developed. What do you mean by fully developed? When they say for you fully developed, this means that the profile of velocity, okay, will be maintained the same. It's not changing anymore with cross section. So here, for example, if I take a cross section here, or here, or here, for all cases, I will obtain this parabolic profile, okay? So here, since I have a constant cross-sectional area, then the velocity magnitude variation will be the same everywhere. So V maximum will be the same for all cases. So I have exactly the same values for velocities across my cross-section. And these velocities are just varying with what? With R. And we said already this is the case for a viscous laminar flow. So I have a laminar flow, then the velocity profile will be nearly parabolic, okay? And we know we can find the expression of V function of R. So once we know V function of R or U function of R, we'll be able to, by integral procedure, to find the total value of M dot, okay? So now here in this problem, they want us to find what is the pressure loss. Whenever we talk about a force, okay, then think about the momentum equation, the conservation of momentum through the control volume. Because pressure is pressure times area will give me a force. So what I am interested here, I am interested to find how pressure forces are varying through my system, okay? So I should correlate them. I should write the balance of forces and see why pressure will be reduced. To do this, I can take a small control volume and do the analysis on it. So you can take any thin disk and look at the forces acting on this thin disk. Okay. So the first step in any problem where you want to relate forces is to draw the free body diagram of your system. So as we said, to understand what is happening, you will take a thin disk. So this disk has a cross-sectional area equal to the cross-sectional area of the pipe. And for its thickness, okay, you can take here, you can take a small element, okay, of thickness dz, and you will do interpretation of what is happening across this system, this control volume. So this is my control volume. What is happening is that I have fluxes, momentum fluxes coming in, okay, and momentum fluxes getting out, because due to the momentum, linear momentum expression. So I have fluxes coming in and fluxes coming out. And I want to relate these fluxes to pressure, to forces acting on the control volume. So I have several type of forces acting on this control volume. First, I have pressure, and then I have friction forces. Okay. So first, let us represent these forces. Pressure forces will always be normal normal to the surface, and they are compressive forces, so they will act towards the surface. So I have from this side pressure forces, and also I will have from the opposite side pressure forces. Okay, and since I want to calculate pressure drop, then the pressure will not be the same on both surfaces. Okay, my purpose is to know how the pressure is varying. This is why I will say, since I did a cut at section Z, okay, I have a certain, at Z I have a certain pressure PZ. And now I will do a cut at another surface that is very close to it. So I just will take a small thickness variation, dz. Then I will have a new pressure on this surface. So this surface is at coordinate z plus dz, and the pressure on it will be p plus dp. So I will have a small change in pressure that I want to determine from applying the momentum equation on my control valve. So the pressure on this side is P plus dP. And now what is the next step? I still have forces. What are other forces? So I have pressure forces, but also I have friction forces or shear forces. Because as your flow will move through a tube, when it is in contact with the surface of the tube, due to viscous effects, I will have development of shear forces that will try to oppose motion of my fluid. So as you can see here, we will represent the shear forces over the control surface. Shear forces will act everywhere on the contact surface. So if I represent them here in the 3D view, shear forces will act everywhere on my control surface. Okay. And in this view, in the 2D view here, I will just see them at this level. Shear forces, how to calculate shear forces? You know that shear, okay, the shear is a force over an area, okay? So if you want to calculate the shear forces, what should you do? You should multiply the shear stress by the area, okay? So here, the total shear force acting on this control surface is equal to the shear tau W, okay? Since we are considering a very thin cross-section, then I will have that the shear is constant over this cross-section. So I can consider same shear everywhere because I'm considering a very small part, okay? And therefore, and we'll see here for this application in particular, the shear stress will be the same everywhere. You know why? Because here the velocity profile is the same everywhere. And you know how to calculate shear? If you remember how we calculate shear, shear is calculated as viscosity times del U by del R. So here, the velocity is varying with R direction, okay? You have gradient of velocity along R. Shear forces at the surface level can be calculated by doing mu times del U by del R at the surface. So del U by del R will be the same everywhere. Why? Because you have the same velocity profile everywhere. And we are dealing with here a Newtonian fluid. The viscosity is constant. So mu is constant. And the profile of velocity is the same. So del U by del R will be the same everywhere. So this is why tau in magnitude. So if of course, you have here for del U by del R, it is positive for some locations, negative for other locations. But in absolute values, the magnitude of shear will be the same everywhere. So this means that here, to calculate the shear, all I have to do is to multiply tau by the area of concern, which is the control surface M. Since here I'm considering this small volume, my control surface will be this one. So it will be equal to the total surface here, of course, and here. So how to calculate this control surface? To calculate this control surface, I just have to do the perimeter, which is here 2 pi r, times the thickness, which is dz. So the thickness here is dz. So I just have to do 2 pi r times dz. Okay? And of course, this analysis can be extrapolated to any geometry. Here we are considering circular ducts. If we have, let's say, square duct or any type of other duct, you just have to replace 2 pi r by the perimeter p. So to have a general demonstration, we will put a function of a perimeter p. If it's a circular duct, then you replace p by 2 pi r. So now, after having presented all my my forces, now I am ready to write the momentum equation. Okay. So when we write the momentum equation,